the Center for Nanophotonics at AMOLF. AMOLF is one of the NWO institutes, the one for functional materials science. And the names on the left, you see, are my co-authors, PhD students and postdocs at AMOLF in my group. And also in other groups. Down at the bottom, I've listed Femius Koenderink and Eric Garnett. They're also group leaders at AMOLF and contribute to this talk. And let me switch on my pointer. On the right-hand side, you see international collaborators. I won't list all their names, but you will see them come by as I give the talk. I put the names of the students and postdocs in these groups that contributed to the talk. So yeah, I called it electron beam spectroscopy for nanophotonics because what I'm going to introduce to you, if you're not so familiar with this, is how an electron beam is actually a fantastic source of optical excitations. So in materials science, when we do optical spectroscopy, of course, we use lasers and they have nice single frequencies and we can focus them down to the diffraction limit. But as I'll show you, a moving electron and that moving electron point charge is also effectively an oscillation of electric field because of the movement of the electron. And that can couple to materials and then excite them. And then we excite optical excitations and resonances. And that's going to be the topic of my talk. And I very much realize that the core of your group is microscopy, and you all have very expensive, not all. I mean, some of you have very expensive Titan microscopes or other microscopes or electron microscopes, but they're usually TEMs, I think. And today my work is going to be mostly working in an SEM. And I show you in some examples why it's nice to work at lower energy in some cases. So it's about cathode luminescence. That's the radiation that is generated when an electron beam hits a surface. And that's a very old technique. I mean, geologists already do this since the 1970s. They take a piece of mineral and they like to know what is it. You put it in your SEM and then you can make your SE image, but also you can make a map of the radiation that comes out. And that's two pictures on the left, and not from our group's work. This is from geology groups. They take a piece of calcite and then the color reflects the emission of the color of the light coming out, and that's how you identify a mineral. Look at the scale bar. It's not so easy to see here. It's 100 micron. That's, of course, typical grain sizes that often play a role in geology. Now, fundamentally, the radiation process that creates here these images is incoherent. It means, if you see in this cartoon, an electron comes in, it creates electron hole pairs in there, and they diffuse around, or they excite defect states or rare earth ions, like in this case, and then they emit, and then the light comes out. And incoherent means there's no phase relation. There's no relation between the time the photon comes out and the electron comes in. And then this circle on the top here reflects the angular distribution. If you have isotropic emission inside, then at the outside, this reflects the amplitude of the emission as a function of angle. This is actually an example of CL on a gallium arsenide wafer. So here you see it peaks at 850 nanometers. That's the band gap luminescence of gallium arsenide. This is a well-known way to do CL microscopy on 3.5 semiconductors. What I will show you in the second part of the talk is there's also coherent excitation. And this is very interesting, just from a very fundamental point of view. And it's very simple conceptually, because you all know the electron is a negative point charge. And that means it induces an image charge, a positive charge in the material. That is a metal, but it can also be a dielectric. There's always this image charge here. And these two charges together form a dipole moment. And we know from optics, if we have a dipole moment, it will radiate. Right? Any optical experiment you do is just because you polarize atoms in the material that create dipole moments, they radiate. And we sometimes call that reflection or transmission. And that radiation is called transition radiation. So every electron that hits an interface, no matter what, will generate this dipolar fundamental transition radiation. And that is coherent. There's a phase relation between the moment that the light comes out and the electron comes in, because the electron is the dipole that generates the radiation. And in this particular example, the angular profile of emission is that of a point dipole sticking up in the z direction above a surface. That's these tilted lobes here. So much for introduction of cathode luminescence. And coming back to this length scale, the 100 micron, that's what the geologists typically work with, as I said. But we in our lab, we are studying light at length scales below the wavelength of light, below the optical diffraction limit. We really wanted to do this CL at extremely small length scales. And it turned out the commercial CL instruments that were available at that time could not do it. So we developed our own CL microscope and developed a few essential elements in it. Let me first show you this here. This is, or maybe the cartoon up here. How does CL work? You come in with your electron, you hit your sample, and then there's a parabolic mirror in vacuum that collects the light. There's a lens, and it goes to a spectrometer. Right? The electron beam scans over the surface to take the SE image, and at the same time, you also make an optical image. That's what you see here. This is a parabolic mirror. It's about 1 centimeter in height. That is here between the pole piece and the sample. You see it blown up. This little hole here in the back, that's where the electron beam goes through. And the whole thing is put on a piezoelectric stage. And that's now where the nanophotonics comes in, because now we're able to focus the electron beam and also the light collection optics at an extremely small length scale, so we can really do imaging of structures that we make in our clean room that are of nanoscale size. So another innovation that we put here is angle resolved CL measurements. So if light comes out under a certain angle, in this optics geometry, it projects at a certain pixel on the camera. Every pixel has a unique relation with some angle of the light that is emitted. So an image taking on the CCD camera directly is a radiation angular distribution. And as I'll show you later, that also means a band structure, optical band structure distribution. So this is how we started. We developed the stage, also all the optics to collect and do these measurements. And then later we founded a company, Delmic, that turned this into a commercial product. That's the little box you see here, or little, it's about 30 centimeter in size. It has all the spectrometers. And so now typically a CL microscope like this looks like the photograph here. This is a Thermo Fisher Quanta SEM. And then the blue box at the end here has all the spectroscopy that collects and analyzes the light. This is what it looks from the inside. This is a SE image taken from all these elements that we put inside there, and we can recognize the parabolic mirror with the little hole. Here's the EBSD, the EDX detector, optical window, the SE detector. You see it all reflected there, literally, electron reflected. So let's start with a relatively simple example. This is indium gallium nitride quantum wells embedded in gallium nitride. You see the cross-section TEM here, beautiful TEM done by Sonia in Delft. Thanks again. And now we come with 10 keV electrons. Here's the casino simulation. So of course, completely different than in TEM. Electron creates this big cascade and electron hole pairs are moving around and then trapped in these quantum wells, and they give CL. And so we get an indium gallium nitride quantum well emission, and we get gallium nitride emission from the substrate. And we can do these measurements as a function of electron energy. So at 6 keV, we mostly see the quantum well luminescence where the cascade overlaps with the quantum wells. And the higher we make the energy, the deeper the electrons penetrate, the larger the contribution also comes from the gallium nitride substrate. Now, this is a pretty conventional type of CL, but this is a start. This is how people in 3.5 semiconductor technology use CL all the time. Now, the next thing that we added here was, can we do time resolved measurements? If we know this, we want to know the spectrum, we often want to know also the lifetime and image the lifetime. So an innovation to the microscope is we put this electrostatic beam blanker in here. It's a standard component that Thermo Fisher manufactures that we included in the SEM. And then there's just an electrostatic potential, 5 volt, that is oscillating here, and we can set with a function generator. It goes up to 80 megahertz. And that means we scan the electron beam here, and here's a very small aperture that we added, the low pressure aperture here, 70 micron. And the beam basically scans over this aperture. And if you set this right, and this was not trivial because the electron beam optics was not initially made to do this, because you want to have a crossover, you want to have a focus of the electron beam here in the, also here in the blanker plates, and they were not in conjugate blanking conditions initially. So we set quite differently the settings of the source and the extractor. If we do it right, we can actually get pulses. Here we measure the, this is measured the transition radiation of an aluminum sample or gold sample that we put down there. This is a way to measure the pulse duration of the electron beam. And at 5 keV, we have the best control. We can make 30 picosecond electron pulses. So that's the shortest pulses we can work with right now, which means we can now do cathodoluminescence lifetime imaging down to that length scale. I'll show it in just a second. So that's lifetime. Another interesting feature, and that's really a new thing in CL microscopy, is the phenomenon of photon bunching. So we know anti-bunching. If we look at single photon emitters, they will never emit more than one photon at a time. So if you look at the statistics of the photon emission, you will see this dip in the correlations between the photons. In CL, it's the other way around. So an electron comes in, it generates a cascade, lots of electron hole pairs that travel around. Some of them create excitations in these quantum wells, and they emit light. So multiple photons come out, but they all come out at the same time. It's one electron that generates multiple photons coming out. So if we now do the statistics of the photons that come out, so what does that mean? So the electron beam comes here to the sample, light comes out, first photon goes to this avalanche photodiode, and then we have a correlator that gives a click and says, okay, I've just recorded the first photon. Then comes the second photon, and maybe it goes to this avalanche photodiode, comes the second click. And now we make a histogram of the time difference between those two clicks. And that histogram is the graph you see on the right side. So normally in incoherent light, this histogram is flat. You can have all kinds of time delays between photons, and the G2, that's this correlation function, is 1. But here you see it strongly peaks. It means photons like to come out at 0 delay or at longer delay. That's the lifetime basically of the emitter we're looking at. So this was first discovered by Sophie Marais in a TEM many years ago. And we concluded that, actually Sophie became a postdoc in my group, in the SEM, because then we have more control over the light collection and also over the current to do these experiments. And so here you see G2 measurements for different currents. So what happens? If we do more and more electron current, gradually these correlations go away. And the reason is not that we don't see this bunching, but we normalize out the background, and the correlations of the background go with the square, right? It's correlating two electrons, goes with the square of the current. So the more current, the less easy it is to see this bunching behavior. And that's the behavior here. The bunching goes down with increasing current. And we just have a paper out that has an analytical model. We don't need to do Monte Carlo simulations anymore to show that this G2 should go as 1 over the current. And it tells us something very fundamental about the number of bulk plasmons that are generated by these electrons. So fundamentally, we think the electron beam comes in the cascade, it makes bulk plasmons, and from there we get electron hole pairs, and then the light is emitted. So that's G2, and this bulk plasmons, they tell us something about how efficiently we excite the material. And so the last example I want to show about this incoherent CL is now we use these lifetime measurements and these G2 measurements to learn something about excitation characteristics in quantum wells. So here you see a top view. This is a nanowire of indium gallium nitride again, in gallium nitride. And if you look at the top, you see these hexagonal facets. And if you make a CL map, and this is now what we do, by scan the electron beam, it's the same sample, we clearly see emission of the quantum wells, but we see these spokes. You see these dark bands here that overlap with these facets here. These are tilted facets. You can't see it on this image. So now you can ask yourself, if you want to make these structures, you want to make lasers or LEDs out of them, why are these bands dark? Is that because the gallium nitride is not emitting? Or is it because the gallium nitride is not excited by the electron beam efficiency? And you don't know, right? If you have the CL map, it can be both. And so now the trick we have developed is we can make a lifetime map. So every pixel in this image, we do a lifetime measurement. So here you see lifetime scale up to 2 nanoseconds. Also, at every of these pixels, we take one of these G2 correlation measurements. So this is a map where every pixel is the amplitude of one such a G2 spectrum. At every pixel, we repeat this correlation measurement. And then we have a model that tells if we know both of these numbers, we can get out what's called the excitation efficiency. It's how efficient is the electron beam actually generating our material. Okay, this is lots of detail, and I don't want to go into it technically. But basically, we found out that these spokes here, the reason this is dark is not because the gallium nitride is bad, but it's because the electron beam excites it less efficiently. And it has to do with how the cascade overlaps over these tilted facets at the surface. And that's important. So it's, the material is not bad. It's just, it's not an artifact, but it's a consequence of the way these wires are excited by the electron beam. So that's incoherent CL, and this is all enabled by the fact that we have now this piezoelectric stage and also this, the optics that we have added to the CL instrument, this G2, the lifetime, and so on. Now let's move to coherent CL. Very interesting from a fundamental nanophotonics point of view, because really we look at the electron beam as a light source in a way. It's just an oscillating dipole that we generate by the electric field of the electron, and it radiates into the far field. I told you we expect this dipole to give these radiation lobes to the side. We've actually done that experiment. We take a single crystal gold sample, come in with 30 keV electrons, and this is the angular profile. So remember in the beginning, when I introduced the microscope to you, we had two settings. We scan over every pixel and we take a spectrum at every pixel, or we look at the angular distribution of the emission by projecting it onto a CCD camera. And here's an example of angular distribution. So the more yellow, the more intense. This is center here, that's going up. It's actually light going straight through the hole in the mirror going up. And this is a donut type, we can make a cross section here, donut type distribution of radiation coming to the side. And these are measurements. So the colored graphs are measurements and the dashed lines are the calculations. And it tells you it's very elegant electrodynamics in a way, because everything is known. It's just optical constants and the electron energy that determine what you see here. And we know the optical constants of gold, we know the electron energy, that's why the model fits the data so perfectly well. Now let's look a little bit more fundamentally in what this coherent CL really means. And there's a lot of data on this slide, so I'm going to take time to explain it to you. So let's assume we have a small particle here, a silver nanoparticle, say 50 nanometer in diameter, and here comes our electron. So what's happening? The electron has a negative charge, so it creates this polarization charge in the nanoparticle, and that creates an electric field in itself, right? So we have charges, free charges in the gold. Every gold atom has one free charge roughly in here, so there are plenty of free electrons, and they're starting to oscillate because the electron pulls on them. And the color plot here is the electric field resulting from that oscillation, right? So positive means negative, maybe blue means positive fields pointing upward, and red means a negative field pointing downward, right? So this is called optical near field, right? This is just completely different than a plane wave of a laser that shines onto a sample. This is the local electric fields. They're optical fields. They're oscillating at an eigenfrequency of this particle in the visible that are just about a few 10 nanometers or so about this particle. But they're induced by the electron. But then in turn, as the electron passes by, this field also acts back on the electron, right? So actually the electric field as the electron comes by that it experiences is, due to what it induces itself. That's what you see here. This is the electric field that the electron feels. It first comes in, it's a small field up, then very close, a negative field, another a positive field, and then electron passes by. So the electron is really slowed down and accelerated by the electric fields that it generates by itself. And so fundamentally, in the end, that can create energy loss, and that's called EELS, which many of you do in your electron microscope. It's just because the electron loses energy by, the retarded fields that are induced by the electron itself. And at the same time, this particle will radiate into the far field. This dipole moment will radiate. That's called cathode luminescence. And both these processes happen at the same time. And the probability for this to happen is just the integral over this curve. So it's the integral of this electric field that you see plotted here over time or over the trajectory of the electron. That integral is slightly non-zero. It's hard to see from this graph, but that slight non-zero effect is creating the EELS or the CL spectrum. Right. So that's a classical description, but in the end, it's a quantum mechanical phenomenon. The electron either loses energy or it doesn't, and the probability for that is given by that classical calculation. So let's see if that works in practice. So here we take a gold nanoparticle, here 50 nanometer diameter, we put the electron beam on here, and this is the spectrum. So here you directly see the radiation from this single dipole moment that is coherently excited by the electron beam. Very strong cathode luminescence coming out. We can now park the electron beam slightly off center, right? Now we can play with the high spatial resolution of the microscope. So we take the particle and we park the beam a little bit on the side. And turns out here's the radiation angular profile. And so this yellow band here means light is radiating to one side. So that's surprising. You would never see this in an optical experiment because you don't have the spatial resolution. But here the electron beam creates this asymmetry. And what is happening is this particle has actually many eigenmodes. I talked to you about dipole moments that are sticking up, but you can also have an in-plane dipole moment in X and Y directions. You can actually have magnetic type dipole moments in the material. And all these modes are coherently excited. They all have a certain phase relation with the electron beam coming in. And they all radiate in the far field to our detector that makes that angular profile. And it's coherent. It means you have to worry about interference. Each of these modes has a phase relation, and that means in the far field, sometimes they have destructive interference. In another direction, they have constructive interference. And that creates this angular profile. And this for us was the first demonstration that we actually coherently excite these plasmons, the fact that we have this angular distribution and these multiple modes. By the way, you see the high spatial resolution, right? This is an optical image. It's the emission at 575 from that single particle. And here's a map with 50 nanometer length scale. Again, showing you, we're doing optics now at a length scale very far below the spatial resolution of the diffraction limit of optics. There's many other things we can play. We can look at the polarization of the cathode luminescence comes out. So we put a quarter wave plate and a polarizer, and then here, for example, this is a bullseye structure that we made by focused ion beam in a gold surface. We park the electron beam here. And now the electron beam creates these dipole moments and also creates surface waves. They're called surface plasmons. It means it's just light that propagates over the surface of the metal. And then the light sees these grating grooves, and it means it scatters out. And by parking the electron beam off center, we create a very complex interference pattern of surface waves that all scatter out and then interfere in the far field. And you see this angular distribution here of polarization. It's very, look, this is the circular polarization, linear polarization. You can have left-handed light and right-handed polarization. You can create light fields that you can never create with optical experiments, just because the electron is a point source and you put it in some engineered surface structure to basically tailor the flow of light, to make shapes in light that you can never make in other ways. That was on metals. So with metals, you would argue, okay, metals are full of free electrons, right? They can, they can couple to the electron and they oscillate and they radiate, and they do, right? But it's also interesting. It also works for dielectrics. Take a nitride membrane. This is, I think it's about 100 nanometer thick silicon nitride membrane with holes in them made by electron beam lithography. It's a photonic crystal. And if you remove the holes or don't make the holes, then it's a cavity for light. So light is trapped. If you make light in there, it's trapped. We make light with the electron beam. So here you see the map. This is the cathode luminescence image. This is the SE image. At the same time, we collect the photons at one wavelength, 690. And this is a map of the light, basically, in that cavity. Right? And this is what's called the local optical density of states, or in this case, it's the cavity mode field distribution. If this was a laser, and these structures can laser if you put a gain medium near it, this would be the mode profile of the light that is rattling forth. This is just standing waves, right? Positive, negative of light rattling back and forth in these cavities there. And look at the scale bar, 300 nanometer. So we're really imaging the shape of light and confined light at extremely small scales. But remember, this is not an active material. This is just a dielectric. This is not a laser. This is not a gallium arsenide semiconductor. It's just an inert material. And what happens here is there's bonds in the silicon nitride, molecular bonds, that are polarized again. They're pulled on by this moving electron. They start to oscillate and they radiate, and that's called cathode luminescence. And the probability by which this radiation comes out is called the local density of states, and that is this cavity mode field distribution. We turned that into a little more complex study. This is photonic graphene, so to say. It's a hexagonal network of silicon disks, actually tour de force to make. They're on a 15 nanometer thick silicon nitride membrane. And you see these hexagons. And now we can make a map of the radiation coming from these structures at 750 nanometer and at 660. And again, is there a length scale here? Yeah, here's a length scale, 1 micron. So these particles are about 300 nanometer or so in diameter. And you see these features here. Here the light likes to sit between the particles, and here the light likes not to see between the particles. This is what we know from chemistry when we have, or from two mechanical oscillators that you couple, right? They couple strongly. You have bonding and anti-bonding modes. So you have a high frequency oscillation and a low frequency oscillation. Here we directly see the bonding field distribution at low energy and an anti-bonding distribution at higher energy. Now I told you we can also look at the angular distribution of the CL. So this is actually projection on the camera. So we shine the electrons on this crystal, and then you see these spokes, these lines coming out. So that's interesting. That means there are certain wave vectors inside the material that can couple out and others cannot. And that means we're probing the photonic band structure of the material. And this was particularly interesting because this photonic graphene is interesting as a topological photonic material. I'm not going to talk about the details, but here we do band structure measurements. So I know this all looks very complex. Let me show you the concept. This was on the left-hand side, a new geometry where the electron beam goes through the mirror, and normally we would have just a pinhole or a slit and a spectrometer. And here we do, but then the spectrometer, what we do in the X plane here, so to say, we disperse the light as in a regular spectrometer. So there we have the wavelength, but in the upward direction, we probe angle. And angle means spatial frequency, wave vector inside the material. Right? And so now we can make a map, that's the map you see here, of intensity of light coming out as a function of wavelength and as a function of angle or wave vector in the material. And this is a theory, and these are the measurements. So we can now actually directly probe the photonic band structure of this photonic graphene. Okay. So then we've talked about light spectra that we can collect. I showed you we can map the lifetime, we can map polarization, angle distribution. We talked about these photon correlations. There's only one thing missing, which is the phase of light, right? And in many experiments, you have some kind of nanophotonic structure and you want to know how it works. You like to know what is the phase front of the light that's coming out, or what's the shape of the phase front, right? And the way to do that, and we also know that from electron microscopy, is holography, right? You have to interfere your beam that you like to study. Let's assume this is a plasmonic resonator, it radiates. We want to know these phase fronts. We have to create a reference and then interfere with the reference. And we have a beautiful reference here because I mentioned to you this transition radiation. The electron beam hits the sample, it creates these dipolar lobes. They're always the same, we know what they are. So now we let them interfere with what we don't know. And that means in the far field, we get an interference pattern. Right? This is how holography works in optics, but also in electron microscopy. And from these fringes, you can know basically the phase of the light. Okay, I won't go into the detail, but as an example, here's a phase map. So the color here is the phase of the light. Light is out of phase on the right side compared to the left side. That's because of a dipole moment, an in-plane dipole moment that we excite in that hole. So that with holography now also we have the phase of the light. So then I want to show you a new microscope that we have constructed to bring the time resolution a little bit further down, namely to 1 picosecond. And here we use photoemission, as you see in the cartoon on the right-hand side, where a 250 femtosecond laser pulse hits the cathode, and then we lower the temperature and the extraction voltage on the cathode, so it's just not giving a continuous electron beam. And then by photoemission, we generate a bunch of electrons that come out, and we can make picosecond electron pulses. And I don't have the time today to show data on this, but we just published the first paper on this nanoscale spectroscopy, where we also do pump probe spectroscopy. It means the laser drives the tip here and then creates pulses, but the laser also goes into the sample and optically excites it. And then we can vary the time delay between the two and pump with the laser and read out with the electron beam or vice versa. And that's all just working now. The last thing I want to show in the talk is going back to this coherent excitation and now more the quantum aspect of it. Because I told you this was all like a classical calculation, but the electron has to decide, am I going to lose energy, yes or no? Right? It's either yes or no, and in the Eel spectrum, either it comes in one place in the bin or in the other. That's the quantum aspect of it. Now we can stimulate that quantum aspect by just enhancing this field. This field is very small when it's made by just the electron. But how about if we come in with a second laser? If we come in with an intense laser, we create a very extreme near field here, then this coupling with the electron can become much stronger. And the microscope I just showed you can do this because it has a laser that drives the tip to make an electron pulse, and the same laser can go to the sample to create this near field. And then we overlap them in time, and then you can enhance this interaction. And we have certainly not invented this idea. This is from Zawale actually in 2009, who for the first time shows this works, and then theory work from Castillo da Bajo and Kosiak, and then a beautiful Nature paper from Klaus Roper's group. This is what happens. If the near field is very intense, then this is an EEL spectrum. So here's the zero loss peak. If the near field is very intense, the electron will pick up quantized single photons, sec2 photons, and 3 photons in energy gain or in energy loss. And this is a quantum coherent phenomenon. For the specialists, it's about Rabi oscillations in which energy shuttles back and forth between the electron and the near field, and you create a whole ladder of excitations. But what's interesting to see is the ground state can be completely depleted, and the electron has picked up these photon energies. That's pure quantum. It also means that the wavefront of the wave function of the electron is now completely modified. Right? So now we're starting to play with the wavefront, both in time and space, of the electron itself. And so that's a new area we're getting into, and I just want to illustrate it with, coming to the end here, how we take a nanostar. This is again a nanoparticle, but now with an extremely sharp tip, so there's very strong optical near field. So we zap it with a laser, create this near field, the electron beam goes through, and then here you see in blue how indeed the zero loss is gone, so that's 200 keV in this case, electron. So this is actually done in a TEM. Has lost all its primary energy, or gained photons or lost photon momenta quanta. So what is fundamentally the strength of this effect? It's this coupling strength. Well, it's like I showed you in the beginning when we talked about CL and EELs. It's the electric field along the electron trajectory that we just have to integrate. So it's just the electron field's electric field. We integrate it over space. And here is omega, that's the frequency where we do the measurement, and the velocity of the electron. Omega over V effectively is a wave vector. So basically, this equation is a Fourier transform. Basically, the strength of this effect is the Fourier transform of this near field at one fixed wave vector, which is given by the velocity of the electron. And I want to illustrate that with this graph here. So if I have a 2 keV electron that is very slow, it's actually 11 times slower than light at the speed of light. So a 2 keV electron is just like light propagating through a material with a refractive index of 11. Very, very slow light. Right? If the electron wave moves very slowly, the spatial frequency between the electron oscillations, as a function, sort of to say, is very small. So the wave vector is very high. 30 keV electron has a wave vector of a little more than 4 there. So we're saying the electron performs a Fourier transform of the near field at just this wave vector. And I can prove that because in the cathode luminescence spectrum at 2 keV, I see a very strong, I see a dipole peak and a quadrupole peak. This is a quadrupole plasmon resonance. And if I go to 30 keV, then I mostly see this dipole resonance here. And the reason is quadrupole fields are very strongly confined. They have very high spatial frequencies. So they will cover best to these slow electrons, whereas the dipole modes better couple to the faster electrons. So it's kind of mathematics. The electron performs a Fourier transform. You have a near field, you don't know what it is. We cannot map it in the spatial domain, but we can map it in inverse spatial frequency. And from that, we can also reconstruct the near field. So with that, yeah, we're probing the near field. And last thing here to show is this color plot. It shows how strong these effects can be, these Fourier integrals. And don't look at all the numbers, but I'm saying the more red, the more interesting, let's say that way, right? And it shows you that the red part is down here. So this is where wave vectors are very large. This is at low energy. So most optical near fields have spatial frequencies that match with this low energy electrons. So for many of these experiments, it's actually interesting to do this in an SEM. Your signals will be larger. Your PNM, your quantum correlations will be stronger in SEM than in the TEM. So that clearly is an interesting direction to go into also in SEM microscopy. So with that, last picture here in the science part. New thing is we also shrunk this whole instrument to a tabletop microscope. This is a tabletop SEM in which we included all the optical characterization. This is a collaboration with Delmic, and we now have a new instrument that's nearly done. It's assembled here by Toon Koenen in the clean room, and can do basically now we're back to geology, but in a tabletop geometry. So with that, where's this all going? We see in meta surfaces these antennas, these plasmonic structures. This is how we got started into it. Quantum emitters with bunching, 2D materials and topological photonics is really interesting to look at because of the high spatial resolution. Tomography, pump probe, and what I showed you at the end. Really, I started talking about the electron as a point charge. And then we did all the electrodynamics. But we know that's not true. The electron is a wave function. It's the Schrödinger equation of the photoemission of the tip that tells there's some probability for the electron to be somewhere in space. So it's a wave packet, right? That may collapse at some point when we start to measure it, but it's a wave packet in space and time. And with these quantum experiments, we now get access to that part of the electron beam itself. And that's a fascinating new area. So with that, I want to conclude. If you want to see more of this, it's also more a technical description on our Erbium group webpage. And like what Sonia mentioned in the beginning, there's a European consortium, and you can see here what we're planning to do together. That's it, and thanks for your attention. I'm happy to take any questions.